All right, let's do this. So the question was, I'm just gonna skip to the good part. That was the extracurricular question. Hello. All right, and so what do we need? Well, we're looking for E, which is Z alpha over 2 sigma over square root of n. Right, we're looking for this. Because if we want to do a confidence interval from this, the confidence interval looks x bar minus E less than mu less than x bar plus E. Right, that's the confidence interval we're looking for. So x bar we have, E we need to find out. Sigma we have, and we have Z alpha over 2. How do we get Z alpha over 2? What is Z alpha over 2?
Just divide the other one by 2, or alpha. Oh, it's 99 minus 1.
No. We're talking about alpha. I'm asking what Z alpha over 2 is. What is it called?
That's larger.
It's definitely not that. That's creepy. Don't do it. No. E is marginal of error. Z alpha over 2 is critical value. And how do we get critical value? We get it from the confidence level through alpha over 2. Right? So we know that our alpha equals 0.01. So alpha over 2 equals to 0.025. Yes? So far so good. Sorry, 0.005. I say one thing, I write the other. Okay. 0.025. All right. So we know that if you look this up on the z-score table, we're getting z alpha over 2 equal to 2.575. Is everybody comfortable getting this? There is no shame saying, hey, I forgot right now. I mean, mid-December, when we get to the final, you don't know this. I'm bringing a bell in my hand, I'm going like, shame, shame. Right now, there is no problem. Is everybody comfortable getting this from this? Yes, yes, yes. Good? Positive. Everybody, yes? Okay. So we get, from here we get this. So now we plug it in, and we get yeah. So our confidence interval, which we defined as x minus e less than mu less than x plus e, well, we just fill in the blanks. X bar was this, there's e, and we get 71.22 less than mu.
Why
Yes.
don't you use the p-hat formula?
Because in this case, I'm asking for the average, not the proportion, but the average. P refers to proportion, mu refers to the average or the mean.
So when you find the average, you're going to use this formula. Right?
Yes. There's going to be a complication later today where we're going to add another
Yeah,
formula
I
to the whole thing. But when you're talking about the margin of error, this setup looks very similar to what we had. We had p hat minus e, p hat plus e. So the setup is the same, right? We have a sample and we have a margin of error. Just the question is how you find the margin of error, and what you use for the sample dictates which one you're going to use. And the mode is very, very similar. So what's the answer? It says 71.22. Now what's the answers? Well, this is the numbers we got. What is the answer? There's a difference between numbers and an answer. In calculus or pre-algebra, this would be answer. You box it in and you're good. This is statistics. I need more. I need to understand what this means.
Is it 99% of?
No, we don't know what the population mean is. We don't know what this is. But we are 99% sure it's somewhere between here and here. And that's the whole idea behind this. It's a confidence interval. We are 99% sure it's there. You know, it's like hide and seek, and your niece leaves the shoes behind the drapes. You're 99% sure she's there. Do you know she's there? No, you don't. You just see the tips of the shoes, right? Maybe she's one of the smart ones, leaves the shoes and sneaks around. I was that kid, so. Okay, we're good. Question?
The biggest problem I have is how do we find that formula through deciphering your question? Is when we read the question, we can't decipher it to which formula.
The question was.
This one, like in our extra.
Oh, but this one. It says random sample of 40 students. So far, so good. 40 students means we're big enough. Okay. The average resting heart rate is already telling you we are talking about X bar. Right? That's the average of the sample, right? For the sample was done. Assuming population standard deviation, that means sigma, right? So you already have X bar and sigma. If you are talking about confidence interval, this is the only way you can go, right? And then at the end of this, confidence interval for the average resting heart rate of the population. Again, population, average, that's mu, which is this, right? So what I would do is, if that tends to get you stuck, and it used to get me stuck, what I had is I brought a highlighter and I just go those 4 keywords, and then I know which one to do.
I can figure out confidence level, because I can draw the picture, figure out what the,
You can get the critical value.
right.
Yes.
But I couldn't figure out the second part, is where do I get the number through the sigma? And
Well, so there, right now we have, okay, so till now we have 2 options. We have p hat minus e less than p is less than p hat plus e, yes? And we have e being equal to z alpha over 2 p hat q hat divided by n square root. We have that part, yes? And we have those 2. Yes? That's what we have right now. Which means what? Which means that if we're talking about proportion, percentages, 3 out of 10 kind of right language, type of language, we're probably talking about this. Right, and I'll ask you about confidence interval for the population proportion, right, for percentage of students doing something. That's this part. If I ask you about, hey, sample average, population averages, means, expected number of, then we are talking about this one. Right? Z alpha over 2 for both is gotten the same way, because we get Z alpha over 2 from the confidence level using the z-score table. So this part, easy. N, easy. The question is, do you have P hat or Q hat in your question, or do you have a sigma? That very much limits the questions. Right, in a random sample of 40 students, 72% prefer pizza, right? Construct a confidence interval for the population proportion of students liking pizza. This. Resting heart rate, the average resting heart rate, this one. So what I would do is I would highlight what you have and write it out. Do you have a P hat? Do you have an X bar? Do you have a sigma? Do you have a Q hat? Do you have P? Do you have sigma? Right, write those things out, and then you just take a look at that versus what the formula is that you either have on your formula sheet or your cheat sheet, and right, it kind of limits the choices. Any other questions? No, so far so good. What happened to the good erasers? You know you spend too much time teaching in front of the board if you have your favorite eraser in each classroom. Somewhere. All right. Since we already went over to using proportions, let's try to expand our knowledge of the mean and find the finding required sample size for a given margin of error. Well, again, we take it from that was our margin of error. If I multiply times square root of n, divide by e, and then square the whole thing, so step 1 will be and then square root. And that's our formula. Again, I started from here, multiply times n square root of n on both sides, divide by e, and then square the both sides of it. And there's a formula. And how do we use it? Well, again, you plug and chug. Example. I know you guys are excited about examples, so example. And right here, it already tells you if you want to do proportions or means, because it tells you mean right here in the question, which means this. Right, because we had the required sample size for proportion, it looked differently.
Is that JQ?
Yeah, is that J or I?
IQ.
Oh, okay. It looks like a J.
Yeah. for me.
Oh, I go my, since my name is starting with a J, my J's are usually spectacularly big. I have to put my ego somewhere.
In the pocket.
We want to construct a 95% confidence interval for a mean of IQ scores. Assuming population standard deviation is 15, we want the sample to be within 2 points of population mean. How big does the sample need to be? Again, the idea is the bigger the sample, the closer the average of that sample is going to be the population mean. Right? If we just take one person and we measure their IQ scores, it can be all over the place. But the moment more people we measure, the more we grow our sample and the average of it, the closer that's going to be to the population mean. And eventually when we ask everybody, we're going to achieve population mean. Right? So how far we want to be? Well, we want to make sure that X bar is within 2 points away from the population mean.
Plus or minus 2.
Oh, plus or minus 2, yeah.
Oh, gee. I gotta go home. Oh, that's good.
Yeah, we're bringing this down. It's depressing. You guys have to look at me, I have to look at the weather. All right, so how do we do it? Well, again, we're going to use this. So we need to fill in the blanks. Well, we have Z alpha over 2 to figure out. We have sigma to figure out. And we have E to figure out. So let's start with the easy. E. How much is E?
E? 2, right?
Yeah, E is 2. And here's a warning. Depending of if you're dealing with means or proportions, you're going to get a number or a percentage. Right? If you have a percentage, if it was within 2%, you need to change that to decimal places. Right? It's just saying 2 points, then it's 2. Right? So you have to be very careful here. Sigma? 15. So sample, that's population standard deviation. And what's Z alpha over 2?
You have to use CI 95%.
So 1.960.
Yes. How do we get that? Well, we went alpha equals to 0.05, which means alpha over 2 equals to 0.025. And if we look up this as the area on the Z table, we're going to get negative 1.96, which is that. Is everybody comfortable getting from here to here? Everybody, yes. So there will be no surprises. So if I decide to, say, have a quiz on Wednesday, that's not going to be, oh my God, how dare you. Okay.
Can I do another example? Just in case. Just one.
Oh. Right, so n equals to z alpha over 2 sigma divided by e squared, and I came out to be that. And the question is that the correct answer?
So is it Z is one
That's
point
correct.
times 1.96 times
15 times 15 divided by 2, and then the whole thing is getting squared.
That's correct.
So this is the answer to the question.
It'd be 20 or 217.
217, yes, because you can have a 9% of a person. We talked about it last week, right? I don't know what your love life is, but ground up in a freezer and then dispensed by percentages is a bad way to go. So the answer is N. Why? Because if we round it down and we do the calculation again, this is going to be bigger than 2 points. This is going to be smaller than 2 points. If we round it down and to 216, it will be bigger than 2 points. So we round it up. Again, think about it as a potluck barbecue. If 20 people are coming, you're not buying 20 plates. Okay, cool, that's done. Okay, let's do the fun part. Let's do the real fun part. I'm gonna start erasing it. Remember when we did a central limit theorem and I told you that we cannot do case number 3 when we don't know the population standard deviation? We can. We are going to do it. So, estimating mu estimating mu when sigma is not known. And I'm going to start with a very obvious statement, and the very obvious statement is if you don't know sigma, you can't use a z-score. I'm going to start with a very obvious statement. If you don't have sigma, you cannot use z-score. So there was a guy at this brewery, I think it was Guinness. It's a small brewery, that they make a half a decent product, beer. And he wanted to do statistics on the beer. The problem with doing statistics on beer, we require z-score to do statistics, which means we need a population standard deviation. If we need population standard deviation, which means that we open every beer, every keg, and we take a sip. How many of you are willing to buy an orange juice that is, 40 ounces minus 1 sip? Or for people that go clubbing, how many of you go to a club and get an open water bottle from somebody, like, hey, drink this? It's good for you, right? Then we run into a problem. We need to check everything. And so this guy wrote a paper about how to do it without having the population standard deviation, and signed the paper student T. Right, so he could publish it without the company getting upset that he's selling, trade secrets. So he signed it as student T. And what we are going to do now is known as the student T score, or the student T calculation, or simply just the T score. So instead of this, we use the T score. So what's required? Well, for the T score, we have a couple requirements. One is random sample. You cannot really have fun without a random sample. Convenient sampling doesn't work. Blind dates among your friends don't work. Blind dates work if they're really blind dates. 2, well, we still need a bigger sample, or sample is from a population that is normally distributed. Mind you, we don't know sigma. So beforehand, we said, hey, these scores were defined as x bar minus mu divided by sigma divided by square root of n. Right, that's what we used to have for these scores. Yes? Yes, maybe. And now we have a problem. We don't have sigma. What do we have instead? What's the closest thing we can figure out to a sigma? The population standard deviation. The closest thing to a population standard deviation is an S. Yeah, sample standard deviation. Right? So the difference between those two is right here. Okay. Well, what's next? Well, critical value. Our critical value was based on what? On Z alpha over 2. But we cannot have Z alpha over 2 because we cannot have Z scores. So the critical value became T alpha over 2. And this is the moment where we pull up our tables and take a look at them. So you pull up your tables, and if you take a look at them, there's two. There's two T-score tables. There's this one, and then there's one on the next page as well. There are two. They're, for the most part, exactly the same. If you look at this table closely, either one, doesn't matter. You look at the column on the very left, that column isn't N, that column is DF. DF stands for degrees of freedom. Degrees of freedom. DF, or sometimes DF. There's the notations depending on which book, which source you have, that those notations differ. You have capital D, small f, small d, capital F. You have a whole set of those. DF, and DF is defined as n minus 1. And now why are we talking about n minus 1? Why we have talking about degrees of freedom being smaller than the sample? Think about a very simple example. So the example we're thinking about is example. We have three numbers that add up to 20. Can you figure out three numbers that add up to 20? That's not very difficult, is it? Right? Every one of you can give me an example. If I give you a 7 and a 5, how many choices do you have for the third number? One. What is it?
8.
So as much as you have a choice for the first one, you have a choice for the second one, you don't have a choice for the third number. That's why degrees of freedom are minus 1. Right? If you play kickball and you're starting to pick members, the last member to be picked for your team is not really a choice. It's kind of like, okay, we're going to get the nerd. And I was the guy. I know a lot about degrees of freedom. Right? So this is degrees of freedom. All right, so what do we do? All right, so let's talk about how to read this table. Regardless of which table you pick, I'm going to talk about this one first, because this setup is much more common across the tables that you find. So you have degrees of freedom on the side, and that calculation isn't exactly very difficult, so we should be very easy to do. And then on the top, if you take a look at the picture, this picture is telling you that they have defined T alpha, what we usually define as T alpha over 2. Right? So because they're only looking at one of the two tails. Usually in our setups, right, we have the bell-shaped curve, confidence level in the middle, and we have two tails on both sides. In this case, they're just talking about one tail here, right? So when we are talking about confidence level of, say, 95, so let's do this. Take this out. Let's put an actual example up, and we can give you the actual
When
example.
we look at DF and we know a number that is given to us in the problem, say n is 20, so we actually look up 19.
Yes. So let's look at doing an example maybe. That'll be easier. An example. Sample 23 from a normally So let's look at a very simple example. Sample 23 from a normally distributed population, find critical value T alpha over 2 for a confidence level of 95%. All right, so let's take a look at it. Well, n is 23, right? Our degrees of freedom are 22. Our alpha equals to what? Yes? And in parentheses, alpha over 2 equals to 0.025. So we look at the table and we say, hey, T of one tail, one of those little tails, the alpha would be this. So we're looking for T of that alpha right here in the middle, 0.25, right? We go down to 22 and we get a number 2.074. Yes? Everybody's with me. So this is how you use this table. Questions?
Why isn't it alpha? We're not looking at alpha, we're looking at alpha.
This table, this is a very common table that you're going to see in most of the textbooks. This table tells you, hey, we define that black area right here, the dark area right here, as alpha. Right? Where in our case, we define alpha as all the pieces missing. Right? So if you're talking about two, in this case, two tails, in your case, alpha would be half of what we have. Right? Now, if you look at the other table on the other side, this table is slightly more convincing. It has C alpha prime and alpha bis on the side here, on the very top. C stands for confidence level, and you can just look up confidence level 95% and go down to 22 and you get it down. Right? Everybody sees. Or you can say, hey, alpha prime, which is one tail, in our case would be this, right? One of those two tails is 0.025. Well, if you look at 0.025, it's right under 95, right? And then you have third option, which is A bis. If you look at the picture, A bis implies two tails, right? And again, it's all in the same column. So you have a second table that gives you more information. It's slightly easier to use because you have the confidence level, but this table is much more common in textbooks. I found both, I'm giving you both. Everybody has a preference for one or the other. Okay. Yes? Yes. Okay. So we got T alpha over 2 to be equal to 2.074.
Question, so what about the third one? Or we're not there yet?
That's chi-squared. That's a whole different
It's out of the
ball.
picture.
No, we're going to get to that, but that's a whole different game.
Look at that.
Why is the alpha prime less than?
No, that's A prime. You look at the pictures,
Okay, A prime.
right?
Yeah.
So if you look at the pictures, it says, hey, this is either left,
Oh, got it.
right tail or left tail, right? Either one or the. This is two-sided.
Okay.
Now we're going to get to left tail and right tail when we do hypothesis testing, but hopefully by then this is not going to be an issue. Right? For now, I don't have a textbook with, for $150, and so you to dwell on it for pages. So you have to believe me till you get good at it. On a side note, I just got a textbook for chemistry. Somebody sent me a textbook for chemistry. Looks like it's going to be about $90. I'm not going to make my students buy it, but I appreciate getting something to level my bed with. Okay, one more example. Right, so let's maybe before we get there, let's expand our knowledge. Margin of error. In this case, it's E. We cannot use Z alpha over 2, so we're using T alpha over 2. We cannot use sigma, so we use S. And then square root of n is the same. If you take a look at this, this is drawing parallels, both between the proportion, when we know population standard deviation, when we don't know it. All of those formulas look very, very similar. The process of getting the answers is very, very similar. You just have to pick the right route to get there. Well, if this is the margin of error, then confidence interval is going to be the same as well. All right, let's do an example. Let's do an example. Okay, so let's look at an example.
The average age of people, what?
Denied.
Denied.
Dean.
Dean?
Denied.
Denied. A little-
Denied a promotion of choice with a standard deviation of 7.2. Assume that the sample, the sample of 23 was taken from a population that is normally distributed. How do we do it?
N is 23.
Okay.
Sigma is 7.2.
Sigma.
Oh, standard deviation.
Yeah, but what kind of standard deviation are we talking about? Are we talking about sigma or s?
It's a standard deviation of 7.2.
Right here. Right, we're talking about a sample of 23 people. This is the average. That's the standard deviation. Yes. So we're talking S 7.2 and X bar at 47.0. if usually, okay, if you want to looking for sigma, you will say population standard deviation is this, or assume that population for all, or sample standard deviation for all the things are this. You have something that will tell you that you're looking at a big picture. When you're just saying, hey, average with a standard deviation, we're talking about the sample. Unless I say, hey, population with this average and this standard deviation. Okay. And alpha, 0.05. So T alpha over 2, how much is that? Yes. All right, so our E is defined as T alpha over 2 as divided by square root of n. And in my case, I get 2.07472 divided by square root of 23. So I get E equal to 3.1. 1. Looking at this because of half. So what you can try to do is just look at here, 95 and 22.
Okay.
That might be easier. At least for starters, when 2 you get used to it. You found it? Good. All right. So we have E. So what's the last one? Well, last part of it is we're looking for x minus E less than mu less than x plus E. So in our case, we are looking at 4389 less than mu less than 50. And here comes an observation I would like to make about this. If you go to the very bottom of either table, the very bottom of either of the tables, whichever one you prefer, you will see that there's 1.645, 1.90, and 2.57, or in that case 6, but 5, on the very bottom, which is telling us that the moment we reach a sample size that is infinite in size, right? Why infinite in size? Because the degrees of freedom are infinite. We are taking a sample that is big enough to be comparable to population, which means that our t-score becomes a z-score. Right? The bigger sample we take, the smaller t alpha over 2 is going to be. Till eventually t alpha over 2 will become z alpha over 2. So that's just a quick observation. Okay, more. Let's do more. Let's do this. If we had that, could we have found the x bar and E out of it? We did this type of exercise for p hat and p. Well, we found x bar to be equal to the upper plus the lower divided by 2, and to find E we went upper minus lower divided by 2. We did that for p hat. Remember? No? Maybe? Vaguely? No, that was before the weekend. Life doesn't start before the weekend. All right, let's do an example. Find x bar and E. So we have 24.065 less than mu less than 27.218. Let's find x bar and E. And while you do that, is do that out. So what did we get for this one? Sorry?
25.64.
And 1.5765? Correct. And having this, we can get to this. Once we have this, we can check if those things make sense. All right, let's look at another example. I figured we can finish this class with crack babies. And I never joke about crack babies. Look, you're asking me where this is useful. What happens if you run a hospital in a poorer neighborhood or one that is ravaged by opiate addiction? Which is getting a very popular thing nowadays, right? Fentanyl, when you need to get your tonsils removed, you get fentanyl as a drug. Yeah, good things. So it's important because if babies are way too small, they cannot handle the required energy productions to keep on developing. So in a random sample of 90 babies born to cocaine-using mothers, the average weight was 2,700 grams with a standard deviation of 645 grams. Construct a 99% confidence interval for population average birth weight. How much should a healthy baby weigh?
Between 7 to 8 pounds, let's say to 9.
Closer to 8, probably, maybe 9.
Depends on what country you live in.
Well, Yeah. Sheer size, I understand, right? I was a heavy baby. But, right, if it weighs 9 pounds, that's considerable amount. 270 grams is not close enough. United States is a metric system, right? But we still use pounds for God knows whatever reason. This is 6 pounds, right? That's short, regardless of which country you go. 6 pounds is getting on really small size. And with considerably large standard deviation, which means that you could be much, much lighter. You could be 3.5, 4 pounds when you get born. That's dangerous, right? So here's the statistics, right? We checked 90 babies. This is what we got. Let's be sure. How sure can we be, right? One of the questions on the homework says, construct a confidence interval if you want to be sure that you only refill the ink for or return the printers for 1% of the customers,
Oh, yeah.
right? 1% of the customers is the alpha. So your confidence level is 99. 99% of the time you want to get it right. So the same thing here. So how do we do it? Well, we start listing things out. I'm going to use my cheat sheet so I don't make a mistake. All right, so we have n at 90, which gives us degrees of freedom, 89 of them. Do we have a mu?
Or 700,
No. Here,
average weight was.
population average. You're looking for population average, right? So we have no mu. How about sigma? No sigma either, because both of those numbers refer to the sample. So instead what you have is x bar at 270 and s at 645. And then we have an alpha at 0.01. Okay, so you look at your table looking for 89. First table, this table won't have it. And the other table will have closer, but it won't have it. It will have a DF of 90. Right? So we're going to have to use that because that's the closest one we have available. So I'm going to, and what did you get?
2.632.
Uh-huh. So our E, defined as T alpha over 2 S divided by square root of N, and I cannot write anymore, N, comes out to be, I have 179.947. Take it right? They rounded off somewhere. I might have gotten the number off a little bit. What did you get? It's punching in 3 numbers.
Yeah, I got 180. 80.6. I cut rounded it off.
Oh yeah,
Definitely got 178.946.
946,
Yeah. 178.
178.
178, 9%.
Okay. That's okay. I mean, I rounded things differently,
That's
right?
telling me.
Again, if you are within, a tenth or 2/10 of a% off, that's okay, right? But if you're off by 2, that's a problem. If you're off by 0.4 or 0.5, that should be okay. I think which means what? Which is the final piece of the puzzle is we have to actually construct the confidence interval. And the confidence interval was defined as x bar minus e less than mu less than x bar plus e. So we add those things up and we get 2, 5, 2, 2, 5, 2, 1, something. Yep, 178. So 270 minus 178, 946. And again, I don't know what the population average of birth weights is, but I'm 99% sure it's going to be between 2521 and 2878.